Hey everybody, this is Larry. This is July 1st here in New York City, the evening of July 1st. And I am here to do one random problem that I haven't done before. So let's take a look. And yeah, at least on Leetcode. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this problem, this video, the solution, and everything in between. And yeah, let's take a look. 1186, maximum subarray sum with one deletion. Given an array of integers, return the max sum of non-empty subarrays with at most one element deletion. In other words, you want to choose a subarray and optionally delete one element from it so that there's still what? It's a lot of words. All right, let me actually understand what it means. Return the max sum with one element deletion. Okay. And I assume they're non-negatives, right? Okay, I mean, there are a couple of ways you can probably think about doing this. I think the key thing to recognize is that the key thing to recognize that you might not remember for this problem is that what is it called? I had the name in the beginning of the when I started thinking, but then I kind of just forgot about. What is that thing called? I'm getting old. I forgot the name, but it's that algorithm is dynamic programming. What is that? Max sum subarray, right? What was it called? Cadence. Okay. So I for some reason, like I know the algorithm, I just forgot the name for some reason. But yeah, and that's the beauty of doing this live, and maybe hopefully you watching it live and be like, wow, Larry's an idiot. But that's okay. I mean, we all could be idiots as long as we don't finish like an idiot, right? We just gotta keep going, and then we get a little bit smarter. But yeah, but the one thing to the observation is that Cadene's algorithm, if you really understand it, is that it is dynamic programming. And what that means is, if you have a good understanding of it, then you could add one more dimension with two states, which is one with zero deletion and one with one deletion. And that's the way that I would think about it. I mean, of course, there are other ways to kind of go about this, but yeah, but that's the way that I think about it. I think I'm curious right now, just like, is there like, I'm wondering if there's a sliding window type thing, but I don't know. And that's the thing with these problems, right? I mean, and it might very well be that there's a sliding window / greedy solution, but the beauty of knowing stuff in general, especially Cadene's algorithm in this case, is that if you are able to kind of figure it out, then you don't have to prove it, right? You don't have to prove it again, because it's just like, you know, Cadene's algorithm, you know the proof, or you may not even need to know the proof, but you know that. I don't know. Next door is celebrating a lot, but you know that there is a proof, and that it is correct. Then just adding to it is not that difficult in theory, at least for me. And I'm just talking about it in terms of like doing contests and stuff like this, right? And or even an interview. I mean, maybe during an interview you would just like talk it through, but during a contest, definitely. Especially since Cadene's algorithm is linear time and constant space. People usually use the constant space version because it's constant space, so it's very easy to make that optimization. But it is actually a space optimized version of a linear space one, which is just something to do. So okay, so what is Cadene's algorithm, right? Let's just kind of I'm not going to do a full review. You should Google this if you really want that, but we can first write what a Cadene's algorithm is, right? So we have like a best is equals, and maybe because it's not an empty, so actually the default set to null maybe should be negative infinity, right? And then you have kern is equal to 0, right? And you have for x in array, kern we add it to x, Yeah, and then we can do best is equal to max best of current. This way we know that it has at least one element. Yeah, and if current is less than 0, then current is equal to x, right? That is just basically, if it's less than 0 with this addition, then we just set it with this being one element. And that's basically the idea of Canaan's algorithm. And of course, this isn't going to work because we get one deletion, right? But this is basically the idea here. You would, with no deletions, you would take the 3. Here, I guess you would just stick to 3, and this is just -1, right? So, okay, so this is what we expect, especially on edge cases, right? And then the idea here is that now we are able to get one deletion, right? So then here, maybe we do current, we just change it to no deletion, and then current, one deletion, maybe. It's a little bit clunky, but and probably during a contest I wouldn't write it out like that, but hopefully it is understandable by people at home, right? So okay, so that means that now you're given x. What does that mean, right? So then now the current no deletion, we can just add x, right? And actually everything will look the same because, well, because that's how we handle it, right? I mean, there's no deletion. I mean, there's no deletion in the other version, so that's why we can do it. Well, how do we handle the one deletion, right? Well, one deletion is, okay, let's just say we skip this x, right, for the current one deletion. Then what does that look like? So then the current one deletion, we just skip x, is just equal to current no deletion. Well, before we make the change, I think. Because here we kind of make the change, right? So that's a little bit wonky. But yeah, here we and yeah, and that's basically the idea. The one tricky thing is just handling. Wait, is that it? Yeah, I guess so. No, that doesn't make sense. Wait, hang on. I'm missing a part where, okay, so this is, so there are two possible ways to get to current one deletion, which is that we either take no deletion, right? And we skip the current element. So this is, I kind of just, so kernel element plus skipping the, so, okay, let me just write, I'm just trying to write out. So skip current element, and then it just means taking the current no deletion element, right? And then here we take one element, which is current one deletion plus x, right? So we take the max of these two, and that's pretty much it. Yeah, and then here max we can just add it to the current one deletion. I think I'm trying to be a little bit careful. We might be off by 1 because because it's easy to be careless in this particular case. Yeah, because here the off by 1 is because current one deletion can have 0 elements, because here this can have, well, I mean, yeah, let's say this has 1 element from the previous one, or actually, it's just that current one deletion can have 0 elements is my point. And that's why this is a little bit wrong, and this is how you get 0. Yeah, and 2 is a little bit wrong too, right? 2 is definitely wrong. How does this get 2? So current one deletion after 1 element, it's going to be 1. We skip the -2, so it's just going to be 1 here, right? And then this is going to be -1. Oh, we don't have a. Actually, let me print it out real quick. I mean, this is generally the idea, but definitely tricky to get right with respect to timing. And the reason is also, to be honest, the reason why this is tricky to get right is because I'm trying to do a little bit too much. And what I mean by that is that I'm doing the space optimization thing, right, before doing the real thing. And it may be, and the space optimization only works if you update things in a way such that things are settled. And in this case, I do not settle it, right? So negative 1. Yeah, this needs to be updated because no, I think this is fine. It's just it's just that this thing it being 0 to begin with is changing. Yeah. I mean, there are ways to write about it, but it's just a little bit annoying. Okay, and this is negative 1. This is just wrong on the no deletion part, actually. This is negative 2 plus... I think, well, this is just wrong. I think I wrote something wrong on this one. So actually, maybe it's not right. If this is less than 0, then we just start with negative 2. And then we do the update for one element. The reason why I wrote it this way is because I want to update it for one element, but I think this is slightly imprecise. Because then now, if then now we just take no elements. I think this is more right, but we have to handle the case where start with 0 element. Or maybe this is actually technically in the beginning. I think that's more accurate. And we have this here so that the max would have 1 element even if it's negative. But it's more precise to have it here because if we have one element that is, we have elements that sum to negative, then we discard to use x, right? So it's something like this actually. And then, oh no, well, this is 0 so that this can happen, right? So it's a little bit confusing, but this should fix it, fix that part. But it doesn't fix the negative 1 part. Wait, oh yeah, and that's because of this 0. And I think more precisely, the way that you would handle it is just that, I mean, I've kind of wrote it this way, but yeah, maybe you could do like current 1 deletion is equal to, we add it to x, right? And then now if index is greater than 0, so it's not the first item, then current 1 deletion is equal to max current 1 deletion current no deletion, something like that maybe, right? Is that right? I don't know. I think if I could, yeah. I mean, I think the idea that I would have wanted to do, and I'm not 100% confident about the way that I did this. This part is a little bit wonky for sure, because I think this is still not even right. I think this should be negative infinity to start. So then now this feels a little bit better. It's just that we don't want, like in theory, I mean, this should handle it. But yeah, I think the idea here is that you would basically make sure that the no deletion has 1 index, and the way that you would think about it is that if you okay, that actually works. That's fine. So this is yeah, so this is linear time constant space, but the reason why the space optimization thing for dynamic programming can be tricky sometimes, because the key thing is about updating the space in a way such that you no longer need them as possible, right? I think the way that I wrote this is that it's very order dependent. The way that there's actually another way to write this, which I didn't do, which maybe I should have done, because the way this is, what I'm doing is kind of an advanced-ish dynamic programming technique, which I kind of did in my head. But I think and it requires a deeper understanding of the order of operations. But the way that I would maybe have done it again is just maybe something like this: previous one deletion is equal to negative infinity, something like that. And then now we can just update current with respect to the previous, right? So then now we can actually write this more clearly, right? In the sense that, okay, so then now we update current node deletion, right? The current node deletion is equal to the previous node deletion plus x, right? Or maybe something like, if previous node deletion is greater than or equal to 0, then we add it to x. Else current node deletion is equal to x. And this is more straightforward to understand, because this is just saying that yeah, if the previous result is positive or 0, I guess. So it doesn't really, if it's 0, it doesn't matter which one it goes, but you get the idea anyway. Then now it updates the current node deletion, right? And then now we want to update current one deletion, and there are two choices, right? One is, as we have done, is previous one deletion plus x, or previous 0 deletion or no deletion, right? And that's it. You don't need to update as a result. And I think writing it this way actually makes it a little bit cleaner, I suppose, because then now you don't need any of these things, right? You have best is equal to right? And I think my base cases are right. I mean, it may be that I still miss some stuff just because of silliness, and it happens, as you know, with me. But yeah, and then now you just update, right? So current node deletion, oh sorry, previous node deletion is equal to this, and previous one deletion. I don't know if this is cleaner to write. Maybe I'll just right. So yeah, let me run it real quick. Hopefully no silly mistakes. Yeah. So this is way easier to understand, I think, and it's still space optimized. It's just that I was trying to be even additional, like another layer of space optimization by using only 2 variables instead of 4. And as a result of that, you have to untangle some of the if you want to call it graph transitional dependencies in my head, and that's why it was a little bit messy and confusing. But as you can see here, this is actually way easier to understand and way easier to write, and still space optimized, right? With only 4 variables. But yeah, but at its core, it's still Cadane's algorithm. It's just that we added one dimension of 0 and 1, and we only need, and then you just kind of figure out the states. And how you figure out the states is just talking aloud of, okay, well, what are the choices do we have? With no deletion, you really don't have a choice. The only choice that you get is that the only choice that you get is whether you're going to start a new subarray from this point or not. And in a greedy kind of way, you always, if it's positive, you always want to keep going. If not, then you do that. And here, yeah. And as a result of this, having a previous thing, you get to set negative infinity as a case. So then now it makes it easier to write sentinel values with respect to best and stuff like this. Yeah. Yeah. And there are some, you have to think for some of the edge cases, like has to be non-empty after deleting one element. Anyway, yeah, I mean, I don't know if this is considered a deep dive, but it is a deeper dive than probably people who've done this. I am curious whether there's a sliding window one or something like this, or greedy, but I don't know. I guess not. People have done Cadane's algorithm. So yeah. What is this? What does backward and forward mean? I don't know. I don't. It Okay, I mean this is the same except for they use different naming. Yeah, I mean maybe there's another thing of doing it, but I don't know. I feel like my way is, I mean I did it live anyways, right? So, yeah, that's why I have this one. Like I said, is linear time, constant space. I think it should be obvious to see why. And yeah, I'll leave it at that. Thanks for watching. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.